in recent years, I was interested in using the idea of subdivision on objects which are not necessarily points. And this is one experiment. And it's a joint work with my student, Evgeny Lipovetsky, who helped me a lot to prepare this presentation. So, since I got 50 minutes, I decided to do a very slow presentation. And I will talk about details also, but not about proofs. So what I will talk about, assuming that not everybody knows what subdivision is, I will give a brief introduction to the topic, but in a way that is relevant to this presentation. So I will present two schemes, which are, in my opinion, typical. And these two schemes are the two schemes that we are going to modify to refine not points, but point normal pairs. Then I will talk how we construct the modified schemes. And for that, I will show you that we need an average and a good average. And the whole idea is that if you have a good weighted average, you can modify in this way any subdivision to refine point normal pairs. So for example, in the case that we refined sets of points, we just had to construct a good average, and then we could do it. And I will talk about the circle average of 2 point normal pairs. Once I have these new schemes, these modified schemes, I want to prove things about them. So we proved convergence, and I will not talk about it, but I will talk on a recent result proving that these modified schemes are generate C1 curves. So let's start. Now, historical remark. Where subdivision was started? It was started from trying to represent geometrically spline curves. Spline curves, this is a linear combination of points times b-spline shifted to the integers. And Pi is a set of, could be finite or infinite set of points in Rd. And this is a curve. This is a representation of a curve by parametrization. Now, in case of finite number of points, if we have a finite number of points, then we have to treat the boundary differently. But since what happens in the interval I plus 1 is affected only by, as you see, because Bm, the B-spline has finite support, 0, m plus 1, then only these points affect what happens on this interval. So in fact, this operator is local, and it's much easier to avoid the boundary treatment, which are very important in application. Not to deal with them, we think about an infinite I. The set I is the whole Z. And that's what I will do here. Okay, so now we can go. How subdivision was created for generating such curves. Let's look at the finite number of points which are cyclic. You can think about it as an infinite set of points if you extend it in a cyclical way. I think we have 5 points, 6 points, thank you. And, I don't know how to count recently. And now, what does a Lane-Riesenfeld algorithm do? This is an example. So first, these are the points that are given, and then they are connected by a polygon, which the points are called control points. The polygon is a control polygon. and then we refine it. So the idea is you refine several steps up to infinity, but infinity is 4 at most. And what is the refinement here? One step of refinement here consists of several sub-steps. So the first sub-step is elementary refinement. We just add the point in the center of the edge. If we will continue to do it, what will be the limit? It's very easy to see. The limit will be just the control polygon. So this is useless. But now we do a smoothing step. The smoothing step, we add the midpoint between the previous control points, and then this is called a smoothing step. And then we throw away all the points except for, we only keep the green points. This is one smoothing step. We keep only the green points. We have not finished our refinement step. We still do one more smoothing step. So we take the midpoints and throw away the green points. Now, you agree with me that this control polygon is much smoother than the original one. Let's go back to the original one. This is the original one, and this is after one refinement step. Now we continue, we do more refinement steps, and we go, let's say, 4 times, and here is the limit curve. You see, it's very nice. It corresponds to m equals 3 to cubic splines. And cubic spline is 1 elementary refinement and 2 smoothing steps. So this is the algorithm for general M. The input to the algorithm are the points and the degree of the spline. And then first we do this elementary refinement, adding point in the middle in between 2 points. In the middle, this is a symmetric average. Then we do this m-1 smoothing step. For the m equals 3, we did 2 smoothing steps. So we replace the old point by the averages between 2 consecutive points. So the sub-steps are counted by L. And then at the end, we put whatever we got after m-1 smoothing steps, we put into the next level. So this is the Lane-Riesenfeld algorithm, which was designed by Lane-Riesenfeld in the 80s, I think, 80-something, 83, something like that. And it was computing curves very good. No theory, you don't need anything. This is an algorithm for computing a known result. And as you remember, the limit was not, let's go back to the limit, okay? It is in the convex hull of the points, but it's not interpolating them. Then David and me decided to see if we can do interpolation. And then we got to the 4-point scheme. We start from the same polygon, and then we keep the old points, but we refine and add intermediate points. So for each edge, we add a green point, and it depends, of course, not on 2, but depending on 2, whatever we can get is something on the edge. But it is depending on these 4 points. And I will show you the rule later. And then we do it for every edge. And then we don't throw away the point. And we keep them with us. So this is a new control polygon. Not bad. Doing now again, we enter the inside point. You see they don't lie on the edge, but a little bit above it. Okay. Now we see the control polygon and the limit curve. And it is C1 continuous, and we don't have B-spline, we don't know what it is. So the only way to approach this function is through a algorithmic, a computational procedure, but we don't have any analytic representation of it. So this is a 4-point scheme. So now the question started, if you want to call it subdivision, what do you get? And then you need to analyze the convergence, the smoothness of the limit curve, and so on. So I'm not going to talk about it. Now I just want to write the 4-point scheme. The 4-point scheme is you keep the old point and you put them in a double index at the next level, and in between you can squeeze in a point between the P2i, Pi and Pi plus 1. This will be P2i plus 1, and you see it's a combination of 4 neighboring points. It is in the interval I plus 1, and you get, this is a rule. But this rule can be written in 2 other different ways that are relevant to our modification. I can write this rule, which is an average between 4 points, by repeated binary averages. So one way is to do this. You see that we have here negative coefficient, which we didn't have in the case of the Lane-Riesenfeld. So we call this extrapolation. And when the averaging weight is between 0 and 1, it's kind of interpolation. So we had here 2 negative coefficients. Here we have 1 extrapolation, another extrapolation, and then we take the average. Another way to do it is first to do the average and then to do the extrapolation. So here we have 2 extrapolation and 1 average, and here we have 2 averages and 1 extrapolation. And we will choose, as I will show you, we chose this form of writing our scheme in terms of repeated binary averages for modifying it to refine point normal pairs. As we can now recall, for the Lane-Riesenfeld, we had it already in a form of repeated binary averages. And we used only the, let me go back. Okay, note, I forgot to note. Please note that the only average that we use in this algorithm is only symmetry average, which gives you the midpoint. So it's already written in terms of repeated binary averages. So now we finished our brief introduction to subdivision scheme, and we go on. I forgot the note again. There is a note here. If we use any one of these 2 representations of the insertion rule, both keep the symmetry relative to the interval I plus 1, and we need only to know how to do average half and average with the white minus 1 over 8. That's all. So now we are coming to our type of point normal pairs. What kind of, this is the usual input for a classical subdivision. Now we add this input. We give the normals. This is a little bit less information than tangents. Because when you give tangent, you give the orthogonal direction to the normal, but you give also the size of the tangent. Here, this is a bit less than giving the tangent. So why do we care about it, let's say, from the practical point of view? I'm interested in it in kind of a more general thinking, but from practical point of view. First, output of modern scanners, you get also normal, not only points, but normal. So why not exploit it? Second reason, if you don't have normal, we can provide you with normals. We can compute kind of initial normals very simply from the geometry of the control polygon. Third reason, and this is the main advantage of these schemes, that I want to show it soon, that adding these normals, we can edit them in the beginning, changing them to get what the designer wants. All these schemes are given to designer to design, let's say, shapes of cars, let's say. So now I want to show this point that the normals give you much more flexibility in editing the initial. So this is what we have. Now I have to show you a video, and this will take me some. Shai, you will do it better. Oh, יופי. Okay, thank you. Okay, you see, you move, up to now we showed you moving points, now we move normals. And the effect is very dramatic on the shape of the control polygon. I think this is it. Thank you, Shai. So this is the motivation for application. So as I said, this is not the first time that in subdivision we refine not only points, but points and something else. For example, in Hermite schemes, we refine points and tangent vectors. As I said, it is a little bit more information. And we are mainly interested in the surface case. And there, the normals are very important. And we do it in a nonlinear way, while Hermite schemes are still linear. Now, the other thing that we were not the first to think about it, there is a paper by Bert Hüttler and a co-author that I will have to make a terrible effort to pronounce his name and to recall it. And then they do also a scheme refining normals, but it's an interpolatory scheme where they give an insertion rule how to add the new point. Our methodology is quite different. Oops, what did I do? Okay. Our methodology is completely different. We don't get one subdivision, but we get a whole family. There's a theorem, and it's very easy to show that you can any average, and this is what are classical subdivision schemes. They take averages between points with positive and negative coefficients. Sum of coefficient is 1. This is a necessary condition for convergence. So every such classical subdivision scheme can be expressed in terms of repeated binary averages. And then we take the binary average between 2 points and replace it by our binary average of point normal pairs. And we will need only the weight half and minus 1/8. For our two schemes that we will modify here. So what is this average? We call it the circle average because if you take data from a circle, you get it, again, the average point normal pair is also sample from the same circle. So we are given 2 points and 2 normals. And now we want to find an average. What is the average of 2 points and two normals? So first of all, we put the normals on the unit circle. And we have to think about them as elements on a manifold. And we will take their average as the geodesic average on the manifold. But then this average is not affected by the point. But for the average of the point, it will be affected by the angle theta between the normals. So we take the bisector of the interval connecting the 2 points, and we look for a point such that, let me go back. We look for a point such as this angle is theta. Okay. Now there is a problem because we could go up and what did I do? Okay, you have 2 possible arcs. We take the short arc on the circle connecting P0 to P1. But we have 2 arcs. How to choose between them? So we have what we call selection criteria. So the first, and it depends on the intersection point between the lines going through P0 and P1 in direction N0 and N1 respectively. This is the point Q. Now, this is the first case. When N0 and N1 are in the same half plane, determined by the line through P0, P1. So they are both on the same side. Then we choose this arc. The arc which is in the other half plane relative to Q. And why this choice is so important, we have a different rule when N0 and N1 are on different sides, on different half planes. Then we look at Q and we choose the arc which is in the same half plane as Q. So we have this selection criterions which guarantee us that the circle average, now let's do the circle average. We go back to case number 1, and now we go omega. We don't have to do half-half, we can take any weight. We go here to point P2, which will be the point of the average, and we go fraction of the angle theta, omega theta. So when theta is half, we will be at the point on the bisector, of course. And the same thing we do for the normals. This is their N2, and N2 is not the normal that you read from the circle. If you take the normal from the circle, then it doesn't converge even. So now what is important property of the circle average that the selection rules were chosen to have? It is that it depends continuously on the normal. We take 2 normals. We start with parallel normals. Now we let the normal go 90 degrees, and then we went, let's do it again. The red point is the location of the point of the circle average. And then, up to now it was continuous. Now we have a singularity at pi. Let's continue rotating the normal and now I will continue rotating it. And so the conclusion is that, it depends continuously and has a singularity at theta equal to pi. But this is okay because also when you do the geodesic average, when the theta is pi, it's not, you don't know where is the average. Let me go. Okay. We went in the unit circle omega theta from n0 towards n1. But if n1 was on the opposite to n2 in the going down, then we wouldn't know which is the short arc. Both of them are equal, and we can't get any result. So since the geodesic average is not defined for theta equal to pi, the whole thing is not defined for theta equal to pi. I think this is the last pyrotechnic. So now it will be a little bit more mathematical. So now we take the Lane-Riesenfeld algorithm and the 4-point scheme, and we modify them and call them M4-point and MLR. So the MLR, one step of refinement is just what we saw, very similar to what we saw previously. Oops. Okay. So first of all, we do elementary refinement, and we enter, these are now not points, but pairs of points and normals. And now we compute the average, the circle average between these 2 points, and we get again a point normal pair, PNP, what we call PNP, point normal pair. This is the elementary refinement, and now the smoothing step, and we have n-1 of them. We are using the circle average instead of the usual average. And this is exactly the same algorithm as I showed you before, one step of the refinement. Now, let's go to the modified 4-point scheme. We use this form of the linear point fork scheme, and we just modify. So first of all, we just copy the point normal pairs from level J to level J plus 1, doubling the index, and then in between we will put this point. First we compute this average, the left extrapolation, and then the right extrapolation, and then we average left extrapolation, right extrapolation, and this is the average. Now, we prove the convergence of both the MLR, and the M4 point. We proved it in a paper in 2016. In this talk, I want to use how many minutes I have? Not many. Okay. I want to use it to show you how we did the C1, how we proved that the curves generated by this modified scheme are C1. We couldn't come up with a proof that would work for every modified scheme. And we just, because it's very much related to the way the two schemes, the scheme is, the control polygon are changing with the scheme. Now, what we show now is that the curves generated by the points generated by the schemes are C1. Why don't we consider the normals? The normals, we know that they are C1. By general result, in a paper by Warner and me, and the results say that if we do averaging when we have a linear scheme written in repeated binary averages, and we replace the binary average by geodetic average and apply it to points on a manifold which has bounded curvature, the scheme is C1, namely the curves generated by the schemes are C1. So we know that the normals will be C1, and we have just to worry about the limit of the curves, the limit of the points which are curves. Now, what is the structure of the C1 analysis? First of all, we have to follow the geometry of the control polygons which are generated by the schemes, the modified schemes. And then the first idea was to use a proximity tool that shows C1 limits that was proved in the paper by Warner and me. But this didn't work. And then we had to extend this proximity tool to take care of this more complicated situation. So what was the proximity tool? The proximity tool was that if you have two schemes, S and T, S is linear and C1, so first of all, the proximity, and then the result. Two schemes refining point, S and T. S is linear in proximity if after one application of T to any sequence of points P, and one application of S to P, we take the difference, this is the difference between them, and D measures the maximum norm of elements of this sequence. This is an infinite sequence. It should be bounded by constant times. Delta P are the differences between consecutive points in P, and D is the maximum of these differences in the norm, because these are points, of course, square. This was a proximity condition. And then we had this theorem in that paper. If S is a linear C1 scheme, namely generating C1 curves, and there was a technical condition on it which I am not going to state. And if T is convergent and satisfy proximity of order 1 with S, then T generates C1 curves. And I checked the proof again, and really we don't have to require it for any P, but only for the P's generated by our scheme. We were looking at schemes for points on manifolds, so we just looked at the point generated by the scheme. Really, in the proof that this can give you C1 for T. So our idea was to use it. So we started looking at the geometry of the control polygons. So we had two important tools that we use. First of all, in order to bound this thing, that's what we have to bound. This is the element at level j plus 1 that was obtained by T, right? We had to show that this point is, we have to look at the maximum of this difference, where Pj are the PNPs generated by T, by our modified, T is our modified algorithm. And of course, this sequence of point normal pairs is consisting of a sequence of points and sequence of normals. But first, to do this was to be able to say what is the distance between a point generated by the circle average and the linear average of the same 2 points. And we need it only for two values of W, half and -1/8. So our main tool was this, and this is completely geometric. We use this inequality and this very trivial inequality and obtain that if you look at P half and that we get by the circle average, right? What is distance from the linear average? We can bound it by a constant which depends on this weight half time theta. Theta is the angle between the normal times the length of the interval P0, P1. And for the omega -1/8, we got a similar thing, just a similar inequality, but with C, with a different C, of course. In fact, we got such inequalities for any power of half. But it's not irrelevant to this, to our talk. So once we have this, we can start following the control polygon and see how the result of the linear scheme differs from the result of the nonlinear scheme. And another result that we used was, I called it the stability of the linear average. If you have two intervals in 2 dimensions, and you take the average between AI and BI with a weight between 0 and 1, and you look at the average generated by A1, B1, and the average generated by A2, B2, the distance between them is bounded by the distance between A1, A2, and B1, B2. So with these two, tools, we could show that if we go to J star large enough, then we can bound the distance between the points generated by our scheme at level J star plus J plus 1. This is a sequence of points at level J star plus J bar 1, minus S operating on the sequence at level J star plus J is bounded by a constant, which depends on the M in the Lane-Riesenfeld, times the maximum of the norm of these differences, times this quantity, which is the maximum of the angles between Ni and Ni plus 1 at level J star plus J. So we have this thing, which is very promising. That's what we were looking for. But then for the theta, which is the maximum of the theta ij, which are theta ij is the angle between Nij and Ni plus 1j, we got that this theta is nicely behaved. It reduces by a factor of half at each step. So it's less than half to the j d theta fs on theta 0. On the other hand, d of this difference between consecutive points in the sequence P at level J star plus J, this happens only for J star large enough, can be bounded by pi over 2 to the power m, half to the J, delta P times this quantity. But if we remember, let me go back to star. You see star, we need that this distance will be bounded by constant time d of delta p squared. And this we don't have. Going back to what we have. Okay, we look at what we have. We have, instead of d of delta of p squared, we have d of delta of p and d of theta. And the first idea was to show that d of theta is less than d of p, then we will get the d of p squared, but it's not correct. So this was a big disappointment, and sometimes disappointments are a good reason to do something else. So the extended proximity condition of order 1, now I will formulate it in terms of, in the way relevant to our analysis. Let T is converging. We know that it is converging subdivision scheme refining PNP. And Pj is the sequence of PNPs generated by it at level j. This sequence consists of two sequences, one of points and one sequence of normal. T is in extended proximity of order 1 with a linear scheme S refining points. If for j large enough, we have that the maximum norm of the elements in this difference. This is application of T 1 time to j star plus j to pj star plus j. This is one application of S. Is bounded by, is decaying like a constant time u to the j, but here mu has to be between 0 and half. And if we have this other proximity condition, then we have a theorem. And the theorem is T is our scheme, refining point normal per S is a linear scheme, and it doesn't have to satisfy any technical condition. If S is C1 and T is in an extended proximity of order 1 with S, then T generates C1 limits. So the idea is to apply this theorem to our modified schemes. How much time do I have? How much? 3? Good. So one word about the proof. How did we prove? It is a variation on the proof that we had in the paper WD. First of all, we showed that if T satisfies the extended proximity condition, then we can show that the mixed smoothness condition of the paper WD is satisfied. This is a mix. I don't think we should go into it. But once we have this decay of the difference of the divided differences, then we could follow the proof in WD, which go from mixed smoothness condition to C1 limits. So the proof is really based on the proof in WD. So let's go. Now we are finished, I think. Now all this condition gives, because half times half, we have decay half of theta and decay half of delta p when j is large enough. And when we put it in here, we get decay with 1/4. And 1/4 is less than half. So this is for the MLR. We have C1 limit curves. Now let's go to the 4-point scheme. The 4-point scheme is much easier to follow because it doesn't have many sub-steps. And we got very similar expressions. And here the decay was 31/40j of the decay in the, let's say, the edge length. This is the edge length. And the decay is 31/40 to the power j. The decay in the theta j is 5 over 8 to the j. And when we multiply it, we get this decay. And by some good luck, it is less than half. So we have also this conclusion that the M4 point generates C1 curves. Again, we don't have a general result. Thank you. I don't, can you, then give him the microphone. This will be much better. Mathematicians are very... No, shout. This is better, shout. Several normals in the same point? This is not geometrical. No, but that's the whole point, that we take the average of 10 elements and write it in terms of repeated binary averages, so that we can always use a binary average. Okay. What? Why? Okay, this is a 4-point scheme. Now there are many other schemes with other negative coefficients, but in the 4-point scheme it's minus 1 over 8. If you want to see it, let's go back to the...
This is an optimal number.
No, it's not an optimum. Okay, here. This is a 4-point scheme, right? This is a 4-point scheme. Now this is written in terms of repeated binary averages. Vladimir, this is also answering your question. This is average between 4. It's very hard to generalize. But average between 2, it's a bit easier. So you can write this average in terms of repeated binary average. First you do this binary average and this binary average, and then you average between them. Similarly, you can do it in a different way, and we chose this way. And I don't have time to explain why we chose it, but extrapolation is better when the points are close. And if you have a converging subdivision, the consecutive points are close, while the second form is using, consecutive points. Here, these two averages are not close to each other anymore. That's why we chose the first. And that's why we need minus 1 over 8. Any more?
All these schemes, whatever constant you take, will produce terms. The motivation for 1 over 8 in the linear case is that it produces cubic polynomials, right?
Yeah, this is a smoother 4-point scheme.
In the circle scheme, there's no true motivation
what I said, that of course perhaps we can.
Why did you consider other?
Okay, I think that this is a philosophical question, something we discuss over lunch or dinner or something like this. So I suggest to take Nira again.
Take away.